finish up more of 12. We want to talk about this idea of synthesis, give you some examples from the course pack of old questions that you should be seeing similar types of next week. And I've been using the word capstone, the idea that this should be the sort of pinnacle of what we achieve this semester. And it really is a measure of whether you're ready for next term. If things are starting to come together, you're starting to see the chemistry as useful, and the steps we use and the sequences that we use are logical, this stuff is fun. And next semester builds on that, takes you into biology, takes you into polymers, stuff like that, much more enjoyable. So looking at a synthesis like this, if you see the beginnings of understanding, great. Next week we'll have questions like this in which you're given 3, 4, 5, 6, 7, 8 steps in the forward direction. And your job is to give the product from each step. Now, fairly straightforward if you've been keeping up. And you can see that the overall transformation in this particular reaction sequence isn't that great. You're just starting off with a fairly simple alkene on the left, and you're turning it into a longer chain alkene. And by now, I hope, after practicing these things, you should be looking for some alkyne chemistry. If you want to make the chain longer, alkylate an alkyne. It's that straightforward. All of this is necessary to do that very simple transformation. This kind of indicates why synthesis is difficult and it's also expensive. There are many steps required there, knowing what you know to get from one molecule to the other. So be prepared next week for this type of linear sequence. You'll be given the starting material, you're given the ultimate product, and away you go. Now, if you're given the product as well, you can work in both directions. You might understand that, you know, the final product is a reduction. So what's the precursor to that? What am I reducing if I'm using sodium ammonia? An alkyne, right? An alkyne. So we've been trying to pick this stuff up in different directions, not just give the product, but think about what you start with. And that will help you with these types of problems next week and also next term. When you understand that, okay, those conditions apply to alkyne chemistry, therefore I need an alkyne. So if you get lost in this direction, often you can make up for it by thinking backwards in that direction. It is very useful. We'll talk today about a bit more retrosynthesis, a bit more thinking backwards, trying to plan things, and often just sitting there thinking about it and scribbling stuff down, often the problem reveals itself. This will be very similar to problems in 3720. You know the answers, you know how to do these things, you just have to prove it by putting things in the right order. So what do you do first here, this type of example? What's the logical thing to do first after you stop panicking? Count. Are we okay with counting? Soccer team? 0 and 1, 0 and 2, that's counting, yeah. We've got this idea now of chain extension. We've got more carbons in the product than we have in the starter material. So that just screams at you at this stage of the game, chain elongation using an alkyne. So we said in the previous example, this type of cis or transalkene comes from an alkyne, right? So what are we thinking here? What sort of chemistry, what sort of thoughts do we have? If I'm starting with a transalkyne as my target, what's the precursor to that? An alkyne, right? So I need to make the alkyne at some point. I scribble that down. I need to make an alkyne. I need to make an alkyne that is larger or longer than the starting alkyne that we have. So I need to do some chain elongation. So what am I thinking of in terms of doing that? How do I make this chain longer? What process do I have to start with? Deprotonation with something such as NaNH2, sodium amide, absolutely. And then we'll alkylate. How many carbons do I need to alkylate with? 3. I'll need something like propyl bromide, propyl iodide in order to make that chain longer. And after that, sodium ammonia, reduce that thing down. And all of a sudden, these things become kind of straightforward. Little puzzles using the building blocks that you've been learning and putting it together in the right order. If you don't get it right, erase it, have another go. You've got plenty of time on Monday. So we deprotonate under basic conditions. We need to be careful with the solvent. What is that type of solvent? What would I describe this as? Polar aprotic. I can't use protic solvents here because they'll protonate the base, and that's a bad thing. So polar aprotic solvent is appropriate to make this. What is this now going to serve as? What's its purpose? What type of species will it be in the next reaction? Nucleophile, absolutely. All that language comes back, and we have to worry about that. If I point that to there and I push this out, what's that mechanism? SN2. So you can see how this all sort of comes back on itself, and you can see how questions next week will incorporate things from different chapters quite easily. This isn't a difficult exam to write, certainly. And what I've got now is my alkyne. My alkyne is finished. I don't need H2O in this because I'm not deprotonating anything in that step. I'm just simply kicking something out, and I'm replacing the H for an alkyl group. And then finally, I'll mix this, and be very careful with this stuff. This looks an awful lot like this, but they are quite different in their chemistry. One is sodium plus, NH2 minus. The other one is sodium metal with NH3. They're quite different. They do different chemistry. So be careful, and away we go. All I want to do today and Friday is wrap this stuff up and think about next week. Any thoughts Any ideas of what needs to happen in this process? Chain elongation, yes. It's not always going to be the case. Be careful, you don't always have to elongate the chain. In this case, yes. How many carbons do I need to bring in ultimately? 2, I think, right? There's the bond that I have to start thinking about making. And this is sort of going into next term a little bit, but we'll start using these little squiggles to indicate where we need to do chemistry, to keep a track of where we need to focus on to be able to make the molecule. So at some point in this game, I need to make that bond right there. I also need to make an alkyne, right? An alkyne isn't an alkene. So when I start out with this stuff, that's quite tricky. How do you make alkynes? You can alkylate another alkyne to make a bigger alkyne, but how do you start to make an alkyne? What do you think now? What sort of processes are we thinking? If we start with that alkene, and ultimately I need to get to some kind of alkyne to alkylate that alkyne to get to there, what do I set this up with? Br2, right? So people are seeing this. You need to put Br2 onto this system, and hopefully by now we're seeing, okay, Br2 adds to alkenes. That's a very simple reaction. And you get the dibromide. And after the dibromide, and you've put the 2 bromines on there, so we've got some molecule like this. We've got 1 bromine here. Not so concerned about the stereochemistry in that because it's acyclic, but I now have the pieces that I need to, there's the cycle. I now have the pieces that I need to eliminate. What comes in next? NaNH2, how much of it? An excess, right? Because that gets rid of both HBRs, but then I need a third molecule. We discussed this in recitation again. The third molecule of NaNH2 inevitably deprotonates the alkyne, and then what do you have to add to get that back? Water. Water. And so you've got this sequence now of putting the bromine on there quite simply by electrophilic addition. We get the anti-outcome, obviously, and then we chuck in enough of this stuff to make it work, and then we put the water in to give the proton back. Okay, more about that concept next semester when we have to be careful in purifying our material to know what we've got. So all of a sudden now we've got this, and now we're ready to do an alkyne alkylation. Haldeman. Yes, you do. You see, you're not in recitation, you see. You haven't had the long, laborious 15-minute explanation for that, right? The answer very quickly for the chemical engineers is this is a super powerful base. As soon as you produce this stuff in its presence, it will deprotonate. You can't stop it. So the product of that reaction is not the CH, it's the C minus, right? In that medium because it's so basic. And then you have to reprotonate it. There'll be more of that next term, and you are in recitation next term. Oh, it's going to be great, yeah. So away we go. We can then deprotonate at the end, and we can set up our alkyl, our alkynyl anion, and then that does the SN2, and there we've got our product, okay? So we're starting to mix things up. You can go from different parts of this book now, different chapters, and get to different places. So we have a toolkit, and we're thinking about when to do what in logical terms. All the chemistry's been done. Okay, give me some comments about this molecule. What words come into your mind? Any words come into our minds? Anti. That's an anti-stereochemistry, isn't it? So I would write that down. Anti. What does that suggest? What is the precursor to this? What starter material, a one step back, gives you an anti-diol? An epoxide. I'm going to draw me an epoxide. You see how this works? Little epoxide. Just to remind myself. I don't know about the sequence yet, but I do know what I need to do at some point. How do you make epoxides? Alkenes, right? So the precursor to that will be an alkene. And what reagents do I need to do that? MCPBA, or in general, the peroxy acid will do that, okay? So that's great. We've got some idea now. So I need to make an alkene. What chemistry do you need to do to make alkenes? Elimination, absolutely, right? So you need to eliminate something. So what needs to be in a molecule in order to do elimination? Leaving group. And all of a sudden we've got back to very early chemistry where we started doing this type of thing, where we had some leaving groups, some proton attached, and scribble something, write something down. It'll drop out. The problem will solve itself. Well, I'm almost there, except this little molecule over here does not have a leaving group attached. So what do I need to do? Radical bromination, right? And if you see an alkane, all you know to do with that, other than burn it, is to do radical halogenation. So that's fine. Now, where does it go? I've got multiple places to go. I could go here, or here, or here. Where do I go? Tertiary. Tertiary. So all of a sudden, things are starting to fall into place. The more you practice this stuff, I hope that you realize that there's only a limited amount of stuff we've done, and you shouldn't be making stuff up yet. So Br2 and heat or light gives us the tertiary bromide. Why not choose chlorine? It's cheaper, but why not use it? It's less selective, right? Why is chlorination less selective than bromination? Chlorine is a much more reactive radical. Bromination is much more selective. transition state arguments, whatever. That gives us a very clean reaction, which the tertiary bromide is by far the major product. Now, why not choose Kotbu? It's too big, and it would give us what product? Hoffman. It would not give us Zaitsev, right? And be careful with the mixing of the names. These are important as clues to be able to help you. You want to here get the tetra-substituted product. Yes, it's the more stable product, but this is not a thermodynamic reaction because it's not reversible. You get the kinetic outcome. And the idea is that you've got a transition state, you've got help from hyperconjugation, and this deprotonation here is going to be the lowest energy pathway, and that gives us the alkene we need. Okay, so we add this stuff, and we get the epoxide. Does it matter in this molecule if I add from the top or the bottom? No, why not? They'd be the same. You turn them upside down. There's a word for this, isn't there? I have made some chiral centers, but does anybody see what's in here? It's meso. It is meso, so people are starting to recognize that. It's good. That's a meso system, and then if I attack from either side, I'll get this, and I'll probably get a racemic mixture of these two, but now I've got my diol. You might not, by next Monday, be able to see this like that. That's fine. You're learning as you go. The idea now is to set up 3720 for those of us who will be there, and to start to think about what to do and when to do it. The sequence of events is just as important as the chemistry you do it in each step. Fair enough? Practice. Do more. Do I need to extend any chains? No. Can I simply add Br2 to my alkene and expect to get that product? No, because it's in the wrong place. Somehow, my alkene needs to get here. So now we do this dance where we move the functional groups around. First of all, I have an alkene. What do alkenes do for the most part that you've seen? They add things. So let's add something to it. What I need to do here is to get that double bond moved to one carbon over so I can put my bromine in the right place. So what needs to go onto this double bond first to be able to start doing that? Put a leaving group on there, right? Put a leaving group on there. Now, does it make any sense to put my leaving group here or my leaving group here? Left or right? Right, that seems to be pretty conclusive, right? That is to the right, because that then brings in the carbon next to it into play. If I put the halide here, I'm kind of back to square one, because if I eliminate, I can only go this way or this way. That doesn't help me get to the right. So if I put my leaving group here, I can then bring this guy into play, and that gives me the precursor for this. So what chemistry are we thinking to do that? Radicals. So what conditions? HBr peroxides, absolutely. So it's fun. It's a game. After we get 50 other reactions next term, it becomes a bigger game. So here we go. HBr H2O2 will give you this. What is the squiggle about? Explain me the squiggle. It's a racemic mixture, right? You've got both of them. Why? It's a flat starting material. It's a flat alkene. Why no squiggle here? Why for art thou squiggle? Why no squiggle? Because it's not a chiral center, therefore squiggle not needed. So here we go. We have a bromine attached. That bromine really doesn't matter here whether it's up or down, wedge or dash, because it's coming out again at the end. We're getting rid of it. We're going back to flat. So why should we use our little friend, not little, is he? He's large. Our large friend, Kotbu. Because you want to avoid attack over here, which is more crowded, and you want to initiate attack over here, which is less crowded. So this thing does exactly that. And all of a sudden, we've got the precursor to our product, where we take the double bond now, and we add to it, and we get this anti-addition of two bromines. A lot of these things are repeating. That's the point. A lot of these things, it's just a matter of when do you do what? That's the key. Anybody got any questions? Everybody all right? Yeah? Okay. Find out next week. This is a kind of a fun problem, because this is kind of, you're limited. You've got some limitations here. And this might be set up by, you can't buy all different types of precursors. You don't have them in your lab. You're in a hurry, and you only have access to one thing. You need to get this done. So what we need to do here is to expand our sort of ability, push our sort of limits in terms of thinking here. I've only got a bottle of this. I can't find anything else in the lab that allows me to build this molecule. I need to start from this, and I need to get all of those carbons in that product must come from that same start material. That's fun. That's much more challenging. So what's the first thing you do, Ashley? What would be the first thing you do here? Nope. You were good at this the other day, Michaela. More simple than that. What's the first thing you do? Count. Count, right? 1, 2, 3, 4, 5, 6, 7, 8. Octane. Gasoline. This is going to be the world's most expensive synthesis of gasoline. right? This is butanol for the chemical engineers, this biofuel, butanol, right? People have decided that biofuels are rubbish, we want to go back to fossil fuels. And you want to make them in the lab. So this is how we did it. I need to make bonds around that carbon, around that scission right there, around that place where I've broken this. I need to get 4 carbons here as one piece and 4 carbons here as another piece and tie them together. Now, what are we thinking when we see carbons being needed to be tied together? Alkyne chemistry, so write it down. At some stage in this game, I need to produce an alkyne, which has a negative charge at the end, and I need to alkylate it. So that means that at some stage in this game, that area of that molecule had to be an alkyne. That's the only way you can do this. And all of a sudden you should start to see now connections. If I want to go from an alkyne to an alkane, what do I add? If I want to get rid of the triple bond and introduce all those, what do I need? Hydrogen gas, with authority. Hydrogen gas and a metal, some sort of catalyst, right? Hydrogen gas and platinum or palladium. So now we've got methods to do that, and now we can think about breaking this bond to give us the piece that we need. I probably would need another carbon there, and that will allow us to get back to a precursor. What does this other piece need to be? If one of the left-hand side needs to be an alkyne anion, what does the right-hand side need to be? Not a carbocation. We didn't do carbocations with alkynes when we knitted them together. You're thinking in the correct way. What real piece, if I have a negative charge on a carbon here, what is the other piece that I need to react it with? A halide, right? So delta plus, right? A halide. So I need to bring in some halide, so I need to make some sort of bromide. So think about this. You've done this in the lab. How do you turn this into a bromide? What do you use? HBr, or sodium bromide sulfuric acid, because you made butyl bromide in the lab, 1-bromobutane. So to make the right-hand side, we need a bromide. To make the left-hand side, I need an alkyne. So what needs to happen to this to make an alkyne? What do I need to do with the OH group? Get rid of it. Maybe protonate it, sure, but get rid of it is the concept. If you get rid of it and that OH comes out, and let's say I use acid or I use a tosylating base, what's the product of that process? If you remove the OH group and remove the proton next door, what do you get? An alkene. All right, so the way we would do this, conceptually, this is a different slide. This is not going to be required next week. This is leaning into 3720 when you have to go back 5 or 10 steps in different directions to get to the pot of stuff that you have to be able to make the product. This is really fun once you get there. So we're now saying that, okay, I'm concentrating on that bond because that is where the 4 carbons and 4 carbons come together, and I'm limited to a 4-carbon precursor. So now I think we go back to this, and then we did the breaking here, and that gives us this with maybe a bromide, and it gives us this guy, which is pretty straightforward, isn't it? Because that just comes from an alkyne, and everybody knows, because you shouted it at me, that alkynes come from dibromides, and dibromides come from alkenes. Fair enough? So we've got some fairly simple chemistry. Now, to think about the leaving group, that's fairly straightforward, because we've got this and we've got this. So to make this stuff, I need to do some cooking. Yes? Go in the basement, go out to your trailer, wherever you do this stuff, and we need to do some cooking. So we get the pots, we get the big pots, and we put them on the stove, and we very carefully start to mix things. In pot 1, you've got to take your alcohol and turn it into that. You've done that. You have made that stuff, right? So that should be known. And now I've got this stuff, I distill it, purify it, I characterize it by infrared or by boiling point or by next semester mass spectrometry, ultraviolet visible, or by nuclear magnetic resonance spectroscopy. Those are really cool tools to do this. But I know I've got the right stuff. In my second pot, I'm mixing some of that bromide, and I'm using this because this is a good E2 process. What's the problem with E1 processes? The carbocations often rearrange and they're messy. So let's avoid that by doing E2 instead. So what we've done here is we've borrowed some of our bromide that we just made, and we've done an E2 reaction. Now thinking about this actually, this is similar to one of the homework questions. Is NaOCH3 a really good choice right there? It is not. Why is it not a good choice? What competes with E2? SN2. And if NaOCH3 looks at that alkyl halide, you'll get both, right? What's a better base to use to avoid the SN2? Anybody? What slows down SN2 reactions? Size. So what type of base should you introduce here to avoid SN2? big base. Anybody want to guess at the big base? Kotbu. So a better choice here would be our potassium TB toxide friend, and this might be a limitation. So maybe we'll scratch that one and put Kotbu in there, because that will give us the alkyne. You going to live, Stefan? Yeah. Good man. At least until Monday afternoon, right? So therefore, you've now got your E2 process, you've got your elimination, you've got your double bond, and then we put the bromine in, and that gives us the dibromide. All of a sudden now we need to do the deprotonation elimination sequence again to give the acetylide anion, and then we put a proton back on by adding water, and that gives us a product which we then deprotonate again to make the anion. What's this mechanism here? SN2 certainly is. How do you speed that up? Add more nucleophile, right? Add more electrophile, bimolecular. So therefore we get the alkyne product, and all of a sudden we're almost done because we can just do the excess hydrogen and palladium, and we get octane. That's where we're going, okay? We're going to start doing divergent syntheses where we have to break things into two parts and make those two parts, and this is an indication of that. Anybody? Okay. People are asking me about recitations next semester. The class technically is full, but there are people who won't be in the class, if that makes sense. Yeah? Not everybody's going to get through this class. So people are signed up, with the intent of getting through, but there will be a few spaces left, so don't worry about being in the class next semester or being in recitations. There should be some space. Now, look at this. What's going on here? We're not extending the chain. What we're doing here is chopping it. We're taking stuff out. What's the only reaction you know that allows you to break carbon-carbon bonds right now? Ozonolysis. People have been studying. Hooray. Ozonolysis allows you to do this, but you now need to worry about where to go to get to that step. You're not going to be able to do one step here because that alkane will just look at ozone and laugh at it. It won't do anything, right? You need to make something else for the ozone to get interested. What's that other thing? What's the precursor to ozone? An alkene. An alkene. So now we're back to the same problem. I have an alkane, nothing going on there in terms of activation. How do I put a handle on there? How do I put an active group on there? Br2 radicals, and that should give me a bromide. And how do you get from a bromide to, because the double bond has to go here. If you can see the bromide, just simply by putting the bromine at the tertiary position, can I use Kotbu? No, why not? It would give the wrong product, it would give the Hoffman product. So which base can I use now? NaOCH3, but that was a problem a minute ago. That did SN2 chemistry. Why am I not concerned about SN2 chemistry here? Tertiary. See how it all makes sense? Marvelous. Love it. So there we go. There's the retrosynthesis. I'm trying to get you ready for next term. There's the retrosynthesis, thinking about what I need in each step going backwards, and then thinking about, do I have chemistry to go in that forward direction? I certainly need to make this, and that comes from this, and I know I have chemistry to get from here to there, and I know I have chemistry to get from there to there, and then ozonolysis finishes the thing off. So it's logical. Just if you know the reactions, this is kind of fun. So there's how you do this. You don't need to split this up into separate pots because you're starting with the whole thing and you're just cleaving it in half. You don't need to bring two things together. So bromine and heat gives the tertiary bromide because of the fact that the tertiary radical is more stable than the secondaries. And then this gives us the Zaitsev elimination to put the double bond in the middle. What would the substitution pattern be on the alkene? Tetrasubstituted. Let's remember that language for next week. With that in mind, we then throw the ozone in. And you've seen this, but we didn't really talk about that in terms of mechanism, but you've seen this in terms of a mechanism where we'd use dimethyl sulfide to do the same thing, and you reduce that thing down, and you end up with ketone. So we've got some nice methods now. We've got a lot to do. We've got a lot of different ways of making things. Carrying on. Any ideas? Any thoughts? You need an alkene. You do. You need an alkene. And the alkene has to go here. That's not so obvious, is it? That alkene is not next to the methyl group. It's going to require some manipulation here. So again, I have an alkane. That alkane that I started with has no functional groups. How do I put a functional group on? Br2 and heat. And where does it go? Tertiary position. So I'm thinking of making this stuff at the beginning. Oops. I'm thinking of making this stuff. There we are. Now it's in the wrong place. That's not including the carbons I need for my alkene. So how do I get this halide moved? How do I move this thing around to get the alkene in the right place? Eliminate first off. What do I need to use here? Big base or small base? Small base, right? Good decisions. And we get this double bond. Now that's not the double bond I need. Somebody said it, what we need to do next, but you've got to be careful in terms of the sequence. I need to get this carbon down here involved. Now, I could do a radical halogenation, but what's the problem with that in that system? If I do an allylic halogenation, what's the problem? Resonance, and what does that lead to? Mixtures. I get product that's tertiary and product that's secondary. So I'm not getting a good outcome. I'm not getting an efficient outcome. So instead of doing that, I need to put my leaving group here. What's the way to do that? HBr and peroxides, right? HBr and peroxides, and after that, what comes next? Elimination with what? A big base or a small base? Big base to avoid going back to the tertiary position and putting a double bond at the bottom. So here's my sort of plan. I need this, obviously, to make the epoxide. It's flat, so it'll give you this mixture up here. To do that, I need this bromide. So I need to put that bromide in. That comes from an alkene. All of a sudden, this carbon is accessible because we started out with this alkene by moving the functional group around. After that, I go back to the tertiary bromide, which is fairly straightforward because that's the major product from bromination of this guy. So you have a 1, 2, 3, 4, 5-step sequence. I said on the final next week, that's the maximum. There won't be more than 5. If you're writing 11 steps for a synthesis, well done. You probably missed the point a little bit. Right? It'll be 5 steps at most. So putting this together in terms of a sequence, you take your methyl cyclohexane, you heat it up with bromine, you put the bromine right here in the tertiary position, you make this guy. You do elimination with a small base. No concern here about SN2 because it's tertiary and it's going to get blocked. And so then we end up with a double bond there. That's the Zaitsev product. And after that, we add the HBr back. I don't really care about squiggles here. Why am I not concerned about all these squiggles when I'm thinking about going there? It's going to go flat again. Yeah, it doesn't matter. It's going to go back to being flat, so I don't really care. And after that, you've got to use the big base. Why not use the small base? Because the small base will put the double bond back between here and here, which we don't want. Use the big base here to avoid this group. And that's logical in terms of regioselectivity. And that gives the double bond right there, which then adds this stuff, or MCPBA, doesn't matter which one you use, and that gives us this. Hooray. Points, passing grades, happiness. Brought to you by organic synthesis. Okay, so what I've done for the last few minutes is brought out, and then Friday we wrap up. Friday we basically tell you how to take the exam. Wednesday, today, we'll finish up with a few examples from the course pack. These are things that are out there. Somebody asked me why there are no answer keys, and the answer is fairly simple. I'm done with 3719 apart from grading the test. I'm in 3720 already, preparing for it. It's a massive job because of all these new requirements we have to get ready for a new class. So I don't have time to do final, well, they're called answer keys. But that promotes you or prompts you to come and ask me some questions. If you're not sure what the answers are, come and ask. Yeah? So we'll see if that works. Now, these are typical, real live ammunition type of exam problems from previous exams. This is what you'll see next week. Make me this from this. How do I get from left to right? What sequence of events need to occur in the lab to get from one to the other? And these are fun. So I need to put a bromine here. I don't have any halogens in there, and I have to be careful here when to do what. So what's the first thing that jumps into your mind as soon as you see this? Food. Sorry, halogenation. I haven't had any breakfast, I'm hungry. Radical halogenation. Do you want to use chlorination or bromination? Oh, a bit of bromination is nice here, isn't it? Because it gives you a clean product. And that will put the bromine here. But that's not the one I want. Okay? If you stop there, you'll get a point or two, but that's not the product. What do I need to do to put the bromine in the other place? Eliminate. We're starting to see this, right? So, big base or little base, so does it matter? Double bond wants to go there. Big base, little base, or does it matter? Little base, I think, yeah? If you'd use a big base, the alkene would probably go there because that's the Hoffman process, and that's more accessible. So then I've got my double bond here. I can't see it. There it is. And then what do I need to do to go to there? Anti-Markovnikov. Using what? HBr peroxides, absolutely. Problem solved. Problem solved. Okay. Now, as you approach next week's exam, realize that you're in organic chemistry. You're not in physical chemistry. You're not in quantitative analysis. If you see people in quantitative analysis this week, they look miserable. Okay? They look really miserable. If you know people in there, you know what I'm talking about. This is kind of fun. Now, the bottom one to me looks confusing. It looks difficult. It looks challenging. That's the idea. I have a methyl group, hello, that I don't have over here. I need to get that methyl group into that molecule. Now, you know, some of you will wave magic wands and whatever, and that methyl group will appear. But those of you who want to be scientists will put it in there systematically and with confidence. What type of molecule do I need to make in this system to do that? Alkyne. That screams alkyne at you. Alkyne! So how do we make an alkyne? Eliminations. What do I need to eliminate from? What do I need to turn this into to do that elimination? What? How many? Somebody said it. Dibromide. You need to add Br2 and you get a dibromide. So these are starting to repeat. That's the point. You only have a limited toolbox just yet. Next term it expands immensely. Okay, so you make this. Then what do you do that? What do you mix that with? NaNH2, how much? Excess. Then what do you do to that? Very carefully you put some water in, because guess what? That's an acid-base reaction. What's the pK of water? 16. What's the pK of the CH bond that you're now producing? 25. There's a big difference, right? 9 units. That's going to be what? Endothermic or exothermic? Exothermic, so you do it carefully. Doesn't get too hot. Don't forget, there's a full page of acid-base chemistry there next week as well. Go back and look at your pKa's, bring them with you for next term. So I'm going to put this on. I'm going to get my alkyne. I think my alkyne is going to go here. And that gives me the piece that I need. I then need to put my methyl group on. So what do I do for this? What do I add to this? NaNH2. Take that proton off, make it a nucleophile. And then what do I need to add to make this work? Methyl bromide, methyl iodide, just the one carbon. And that will give me a system that has an alkyne. There's a cycle, right? And there's my triple bond, and there's my me. How do you finish it off? Lindlar, H2 platinum, or H2 palladium, barium sulfate, and quinoline. And that magically gives you the cis-alkene. So you're just looking at the stereochemistry to decide what to do there. Not too difficult there. Okay, last few, and then we're done. Any ideas? Top one. Br and radicals, okay? Even if you're lost on this stuff, you do enough problems, it'll start to sink in. If it doesn't, okay. We're not going to get very far. But it will start to sink in. There are a limited number of reactions, a limited number of Lego bricks that you can put together so far. What's the first thing to do with that alkane? Brominate it. Put the bromine on there. Then what should I do next? Because my bromine isn't there. It's down at the bottom. What do I need to do from the first bromide? Eliminate. Big base or small base? Small base, right? To get the double bond inside the cycle. Then I'm here. No, I'm not quite there yet, am I? I have a double bond, I think, here. How do you finish it off? HBr peroxides. That's all it is. The nice thing about the final is you've got a chance to make up for previous errors, and you have plenty of time. Have a go. Again, I can't grade thin air or blank space. And it's a waste of a tree, let's face it. Don't leave stuff blank. Answer the questions. Down at the bottom, finish this off. Double bond going to triple bond. Ouch. Any ideas? Now, HBr would work for this, but I don't think it's that clean. HBr would be okay, because maybe it wouldn't. How many leaving groups do I need? 2. And what would HBr put on? Just the 1. So it's not going to work. So what's better than HBr? Br2. Br2 followed by? Blah, 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 blah. Sodium amide, NaH2. Get that down to the negative charge, put the water in, protonate the thing, and there's your alkyne. And that's it. A couple more, and then we're going to talk about the final. Any ideas? What needs to happen? We're trying to teach this. You're learning this stuff. You're new at this. Say again? Alkyne. An alkyne has to happen, so write it down. At some stage in this game, I need a triple bond so I can extend the chain. How many carbons do I need to extend the chain by? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. How many extension? 1. Right? 1. So I need to make this guy, which I already have that. So what do I need to do first? Deprotonate with what? Why doesn't sodium hydroxide work? It's not strong enough. Good, we're starting to see these things. NaNH2 gives you the negative charge at the end. And then what do I need to bring in to put a CH3 group there? Methyl bromide or methyl iodide, exactly. Now, that's not what I'm after. I'm after an alkane. Do I care about Lindlar? Do I care about sodium NH3 in this system? Or do I just hit it with H2PD? H2PD, because that will take it all the way down to the alkane. Last one. I've had a few questions about this in office hours this week. This one doesn't seem to be so obvious. Do I need to bring in any extra carbons? No, you have the same number in the starting material as the product. What type of chemistry am I thinking here? This is tricky. This is tricky because it's not immediately obvious, and there's something hidden inside this process that needs to happen to get to an aldehyde. Any ideas? Tautomerism is in there, right? The big T. There's a big T, tautomerism. What is the precursor to an aldehyde in a tautomeric system? It's an alkene, but it has something attached to it. It has an OH to attach to it. So if you have a double bond with an OH attached to it, what have you got? Enol. It's an enol. So as you approach this problem, you're going to have to make this. Okay? You're going to have to make that. Because that tautomerizes to give this. So you can get these, I'll be very happy. How do you put the OH group on there? Hydroboration. Okay? Hydroboration, you want to go to here, so you're doing essentially an anti-Markovnikov addition. You want the OH group ultimately to end up at the less substituted carbon. So we'd use the parachute, because the parachute is we're going to want to avoid the other end of that molecule. That's the parachute. Okay? So I want to put my there, and I want to go there to avoid the boron hitting these guys. It's the same concept as with the alkenes. It's the same idea. So you do that, you get this. What's the second, or what are the second reagents required to finish that off? You make the boron product, and then what do you do with that? NaOH H2O2. NaOH H2O2, you get the migration, which is concerted, with retention, whatever, and you end up with the enol, and the enol tautomerizes. Those are the most difficult ones because that's not immediately obvious. You've got to be on your toes for those. Well, that is the last slide from chapter 12. I am done with chapter 12. I can do this all day. I'm not done with today, though. I've got 10 American minutes. Between now and Friday, is Friday worth showing up for? I would hope so, because I'm going to tell you how to take my test. I'm not going to tell you what's on my test. I'm going to give you an idea of how to approach it. So by the time you're on page 35, you should have passed the class, we would hope. And you've got enough of the material organized and understood, because we're trying to, that's what this chapter is about, organizing. And then we can tackle 3720. We started off 15 weeks ago from freshman chemistry. And freshman chemistry is, it's an interesting attempt to get people to think about what chemistry does. And because people take different faculty, they take different professors, they have different paces, they come from different high schools, people don't know the same stuff. It's just obvious on the first day. So what we do on the first day of class is we start to think about chemistry as not just a bunch of numbers, right? It's a very, very broad, very big subject that can be understood if you're happy with the periodic table. Okay? If you understand what that thing is about, it's always on the front page of a test. Why is it always on the front page of my test? That's the code that we use to study chemistry. You understand about the periodic table, you can talk about all sorts of different elements and all sorts of different atoms. But obviously in organic chemistry, we focus on carbon and a few elements in the first term. We'll expand that next year, but right now we know a little bit. And we started talking about what organic chemistry was, and the fact that I don't like the name. I went into a discipline in which I don't like the name of the discipline, because organic is redundant. It doesn't mean anything. That was proven in 1828 when Wohler made this thing, urea. It was the first synthesis of a natural molecule that was produced by animals or plants and was made in the lab. You didn't need some vital force or something to be alive to make it. And in that, it's almost 200 years now, we've gone from this type of synthesis in which everything's flat, everything's pretty straightforward, very few atoms, and we can make these guys now. We can do very spectacular, very intricate organic synthesis. But when you first come into a class like this, having done general chemistry, and wherever you do it, wherever on the planet, it's always, plug and chug, calculator, get the answer, get those significant figures right or else. Have we seen a significant figure yet? No, of course not. This is very different, and it's a very, very challenging thing to get into from the beginning. Having done all of that, well, general chemistry to me is very rigid. And all of a sudden, organic chemistry is kind of, fluid. You can choose to do a different synthesis. Your synthesis might be different to mine. And in fact, this is great because there are instances in which a student in the class will come up with a better synthesis than I got. That's great, right? Go get a PhD, right? That's what we're after, is people starting to open things up and starting to expand. So we did this in the first couple of days of class, whenever it was in August, right? Long time ago. And we said that organic chemistry can be managed if you start seriously from the beginning and pick up the ideas along the way. And those ideas included things like shape. What are we thinking about next week? What are the terms that we need to worry about? What are the ideas that we need to be concerned about? You can explain the shape of a molecule quite quickly by understanding the bonding patterns. If you have 4 things attached to a central carbon, they're going to give you a tetrahedron. And that was an sp3 hybridization. Go back and look at your hybridization patterns. There are those on there. Be able to draw sp3, sp2, sp. Be able to populate orbitals for me. That's always on there. And this came about through something that isn't magic. It's very obvious. Valence shell electron pair repulsion theory. They don't like each other. The bonds want to be away from each other. And the furthest you can get 4 away from each other is a tetrahedron. And that was a very simple place to start, and we did alkanes a way back. So those bond angles now, 109.5. If you start to go away from 109.5, what happens to the molecule? Strained, good. These are words I want to hear. It becomes strained. Makes it less stable, might make it more reactive. Those are things we've picked up. And we started talking about lab. Get your lab reports in. If you're one of these people who hasn't got the lab reports in, you might be in for a shock next week. I've done this before in the past. Look on the syllabus. You've got to get a 70 in lab to get through this class. If you don't pass the class. I've had people do quite well in lecture, and they blew off the lab. And they failed, and they take it again. Yeah? Get your lab reports in, get those points, get that grade, and be happy. Looking at these now, we put these up on the first day of class. Back then, they didn't mean very much. It was a whole bunch of wedges and dashes and whatever. Now it means something. In terms of solubilities and properties, soluble or insoluble in water? Insoluble, it's mostly alkane, right? It's mostly non-polar material. What about this down here? Soluble, sugar. Okay, that's what goes into your soda, goes into your coffee. Because we've got this idea of polarity based on electronegativities, based on dipoles, and we can argue that. What's the electronegativity of O? 3 point. Don't forget these things, right? Don't forget these things. If you like getting tattoos, get them tattooed on your hand. Get them tattooed on your head. You'll never forget these things. What is the electronegativity of H? 2.1. So 3.5 and 2.1 is a big difference, right? It's not enough difference to be ionic, but it's different enough to be polar. And so now we have the possibility of polar molecules. So what we'll do on Friday is try to wrap this up by looking at stuff we've done in the past. Hopefully, if you've got questions, ask those questions. But thinking about the exam coming up and thinking about getting ready for 3720, where do you need to be and how do you get there? Okay, see you on Friday.